Hello and welcome to Cognito Key. Have you ever just stopped and wondered how we manage to do these calculations that are so huge they can predict the weather or even power the AI that's changing our world? Well, today we're going to unlock the secret behind that incredible power.
We're living in this world of big data, really complex simulations, and of course, artificial intelligence. All of this demands an absolutely incredible amount of computing power. So the big question is, how do we build machines that can actually keep up with it all? A huge part of the answer lies in this really clever piece of hardware called the array processor.
So, here's our game plan for this explainer. We're going to start with the basics, what are these things? Then we'll zoom out a bit to see where they fit into the bigger picture of parallel computing. After that, we'll get to peek under the hood to see how they actually work, explore their two main flavors, and finally, we'll really get why this tech is so unbelievably powerful. All right, let's dive right in. So, what exactly is an array processor? Well, at its heart, it's basically an engine that's purpose-built for supercomputing.
To really get what an array processor does, first, you have to appreciate the sheer scale of a supercomputer. I mean, we're not talking about your everyday laptop here. These things are computational giants, absolute behemoths designed for one thing: pure speed. They can do things in a single second that might take your personal computer hours, maybe even days.
And this is exactly where the array processor comes into play. Think of it as the heart of the supercomputer. Its secret weapon is an entire army of what are called arithmetic logic units, or ALUs. In this world, we call them processing elements, and their superpower is working together in perfect parallel to chew through enormous sets of data.
Now, that idea of working in parallel is the absolute key here. It puts array processors right in the middle of this concept called parallelism, which is really the art of doing many things at once to solve a problem much faster.
So, an array processor is a type of parallel computer. The core idea behind any parallel computer is actually pretty simple, but it is so powerful. You just use multiple processing units, have them work at the exact same time on the same problem, and you get the answer much faster. Now, there are a few different ways to get this parallelism. You could use something called pipelining, which is kind of like an assembly line for computer instructions. Or you could use multiprocessor systems, which have several independent brains working on their own. And then there's the array processor, which uses spatial parallelism. Imagine tackling a big problem from many different points all at the same time. That's the idea. And this word right here, synchronously, that is the key difference. In an array processor, every single element operates in perfect synchronized lockstep, just like a marching band. But in a multiprocessor system, the different processors can work asynchronously, which is more like a jazz band, with each musician doing their own thing.
Okay, so this perfect lockstep thing sounds cool, but how does it actually work? How can one single command make so many different things happen all at once?
Well, the design is actually beautiful and really elegant. You have one control unit, the CU, and it acts like a general. And this general is in charge of a whole army of processing elements, or PEs. The control unit gives the orders, and the army of PEs carries them out.
The process itself is wonderfully simple. First, the control unit grabs and decodes just one single instruction. Second, it broadcasts that command out to every single processing element. And third, each PE executes that exact same instruction at the exact same time, but on its own little piece of data. They all start together, and they all finish together in perfect unison.
So this really elegant design actually comes in two main flavors. You've got what are called attached processors, and then integrated or SEMD processors.
So first up is the attached array processor. The best way to think about this is like a powerful add-on, like a turbo booster for your computer. You take a regular general-purpose computer, the host, and you connect this specialized processor to it. The main computer handles all the normal stuff, but whenever there's a really heavy calculation, it just offloads that work to the attached processor for a huge speed boost.
The second type is the SIMD array processor, and SIMD stands for Single Instruction Multiple Data, which, if you think about it, perfectly describes what we've just been talking about. The control unit sends out a single instruction, and it goes out to multiple processing elements, which then all work on multiple streams of data at once.
But here's what's really clever about SIMD processors. They aren't always an all-or-nothing kind of deal. They can use something called a masking vector, which is basically a set of on-off switches for the processing elements. This lets the main control unit tell specific PEs to just sit out a particular instruction, which gives it this incredible fine-grained control over the whole operation.
So we've seen the how, but what about the why? I mean, what is the real-world power of having a setup like this? Why does it matter so much?
Well, the payoff is just enormous. First and foremost, you get a massive speed up in your calculations, which boosts the entire system's performance. Second, since every single one of those processing elements has its own little bit of local memory, the whole system gets a huge memory boost. And ultimately, that makes them the perfect tool for any problem that needs an extreme amount of parallelism.
And listen, this isn't just theory. The legendary ILIAC 4 computer was a real-world titan that used this design. It was one of the first true supercomputers, and it tackled these immense problems like computational fluid dynamics that were simply impossible to solve before it came along.
Array processors really laid a critical foundation for the high-performance computing we have today. And as our data just keeps getting bigger and our problems more and more complex, it leaves us with a really fascinating question to think about. What will the next evolution of parallel processing bring us?
And on that thought, we'll bring our exploration of array processors to a close. Thank you so much for joining me today here on Cognito Key.
If this explainer helped you unlock a new concept, please do give it a like, share it with someone who might find it interesting, and of course, subscribe to Cognito Key for more deep dives. Until next time, keep on learning.